So far, we've been looking at how individual data values vary around the mean for a population. But moving forward, we would really like to look at a sample and look at the mean of the whole sample and see how the means of a bunch of samples of the same size taken from the population vary around the population mean. So how do groups of data compare to the overall data? And this is going to lead to maybe the most important topic that we're going to study, called the central limit theorem. And to kind of get an idea of how this works, we're going to do something where we roll dice. And so in this activity here, I'm going to skip down to this link in the last part where it'll walk us through this activity where we'll roll bigger and bigger groups of dice and look at the averages. So in this link, in this first little image, we're just going to be rolling a single die repeatedly. So I'm going to do it once so I can get numbers 1 through 6. And if I click on this repeatedly, there I've gotten a second one. Let's see, if I do this again, I get a 3 and then a 6. And if I kept doing this for a very long time, maybe I'll click on the roll 1,000. If I roll 1,000 dice, I would expect to get about the same number of rolls of 1s, 2s, 3s, 4s, 5s, and 6s. I might not get exactly the same number of rolls of each of these values, but I would expect them to be pretty close. So if I did this a whole bunch of times, I would expect to get about the same number of each value. Now, let's think about what happens if instead of rolling a single die, I roll 2 at a time. So if I roll one pair of dice and take the average between them, here it says I rolled 2 dice, I took the average between them, and there it looks like that's a 5. And so here, since I'm taking the average between 2, I'm not just getting the numbers 1 through 6. I could get other values. And if I do this repeatedly, we want to see what type of distribution we get for the average of 2 rolls. And so now I'm going to roll 1,000 pairs of dice and plot the averages. And looking at this is a different sort of shape or distribution than we had before. Before we had kind of a uniform distribution, and now we have something that looks a little bit more normal. And maybe pay attention to what looks like it is in the center of this distribution, and pay attention to how spread out it is. So what we could say about the standard deviation. So we've done this for a single die, for a pair of dice, and now let's do it for a group of 25 dice. So we're going to roll a pack of 25 dice and take the average. So again, I'm not just getting numbers 1 through 6. This is the average of 25 rolls. And if I do this a whole bunch of times, this also looks pretty normal. And if you look here, it looks like we have something around 3.5 in the middle, but it looks like this distribution is less spread out than our last one was. Our last one looked like it overall went from 1 to 6.5. This looks like most things are closer around 3.5. And lastly, if we take a 400 pack of dice and take the average of all of those rolls and do this a whole bunch of times, this also looks normal, but it looks like the standard deviation is getting smaller. And so try to think about what is happening as our sample sizes are getting bigger here. Is the mean changing? And is the standard deviation changing? And that's what we're going to talk about. So before we get into any calculations or anything, the big idea of the central limit theorem is explained well in this video here. And so the about first 16 minutes of this video are helpful to watch. So I'm going to include the link to those, or you can go to this link in the notes and watch the first 16 minutes of that video to get started talking about this idea of the central limit theorem. So what we saw in our example about the dice is with the dice, we started with a distribution that was not normal. With the dice, it looked pretty uniform, but the point was it was not normal when we were just rolling individual dice. And that distribution had some mean and some standard deviation. But now, instead of looking at the distribution of just X, of just that one roll, now we're going to be rolling a bunch of dice or looking at a sample of things and looking at the sample mean. And so we're going to be looking at the distribution of the sample mean. And so this is called a sampling distribution of the mean, and it's a distribution of the mean from a bunch of samples of the same sample size. And the idea here is as long as our sample size is big enough, which we'll formalize exactly what that means later, but as long as our sample size is big enough, then this is going to look normal. And the mean of this sample mean distribution is going to be equal to the original mean, and our standard error or our standard deviation of the sample mean distribution, this is not quite the same as the original standard deviation. We saw that as our sample sizes got bigger, our standard deviation got smaller, and so here we have to divide by the square root of n, which is our sample size. And so in exercise 5 here, it says we have a population mean equal to 250 and a standard deviation of 25, and it says calculate the standard error of the mean for the following sample sizes. So standard error of the mean, that means the standard deviation of the sample mean distribution. So that should be our original standard deviation divided by the square root of n. So in part A, if n is 20, then our standard error is going to be 25, our standard deviation, divided by the square root of 20. And if we plug that into Excel, we should get about 5.59. In part B, it says now use a sample size of 50. So here our standard error would be 25 over the square root of 50. And if we plug this into Excel or a calculator, we should get about 3.536. And let's do this one more time. If we, in part C, instead plug in an n of 80, we'd have 25 over the square root of 80, which is about 2.795. And so as our n gets bigger, these standard errors are getting smaller. As n gets bigger, since n is in the denominator, that will make the overall fraction smaller. So as our sample size increases, the standard error should decrease. So we should be kind of closing in on the mean as our sample size gets bigger. And we saw this a little bit with the dice example. When we were rolling a pair of dice, our distribution had a curve that was kind of normal shaped, but as our sample sizes got bigger, it looked like the curve was really closing in. Most of the data was around the mean. My picture is making it a little bit hard to see, but we still had that mean right in the middle, but most of the data was piled around the mean as our n got bigger.